My presentation is about Brewer operational issues, specifically for neutral density filters, dead time, spectral stability, and spectral accuracy. The present study is focused on the development of new routines and techniques which aim at improving the quality of the final products. So the main goals is to constitute grounds for discussion and ideas for the improvement of the methods and the techniques presented, and the implementation of these methods and techniques on more instruments to estimate the validity and the generality of the results. The first part of the presentation is about deriving the dead time from direct sun measurements. So the main advantage of deriving the dead time from direct sun measurements is that sun is a strong and stable light source for short time intervals, which is independent on the instrument. The main disadvantage is that in cloudy days, the signal may be very low and noisy, so we can calculate a value for dead time. To calculate the dead time from the sun, we created a routine which we implement near the local noon in order to have high signal and slow change of solar zenith angle. There are two main features of the created routine which I should notice. The first is that we use a proper neutral density filter when the irradiance is measured in order to prevent photomultiplier from overexposure and to remain within the linearity limits, and that the position of the micrometer should be such that the counts on slits 2 and 4 are similar. This is because large differences between the counts at slits 2 and 4 seems to lead to underestimation of the dead time. To get similar counts at slits 2 and 4, we have to find a different micrometer position for each different instrument. This position is a function of solar spectrum and of the instrument response. So to find this position for our instruments, we performed near simultaneous scans of the solar spectrum on slits 2 and 4. You can see the results for the double and the single Brewer that we have at Thessaloniki. For the first one, the results are presented with respect to wavelength at slit 3. For the first one, we found that the best position is the 333.5 nanometers, while for the second one, we found that the best position is the 318 nanometers. Here are some results. For the double monochromator Brewer number 86, you can see that, with the red squares, we present the dead time from the direct sun measurements for both instruments, while with the blue cycles, we present the dead time from the standard lamp. For both instruments, we find lower values compared to the nominal ones, while for Brewer number 86, the dead time from the standard lamp is very noisy. This is because of the very low signal. Generally, for this instrument, we have a good agreement between the dead time from the sun and from the standard lamp. For the Brewer number 5, the dead time from the sun is lower than the dead time from the standard lamp, but we have few results, so we have not declared or have an idea for what exactly the reason is. The next part of the presentation is for the neutral density filters. For the purposes of this study, we calculated the ratio of the attenuation for consecutive neutral density filters of the Brewer number 86 using 3 different light sources: the sun, an external 1000 watt lamp, and the internal standard lamp of the instrument. the measurements from the sun at the low attenuation filter were always of the order of 1 million counts per second, while the signal from the two other sources was up to 4 orders of magnitude lower. Here we can see the results. The upper graphs show the ratio of the attenuation for filters 1 to 0, 2 to 1, and 3 to 2, while the lower graphs show the ratio of the results from the internal and external lamp against those from the sun. As we can see at the upper graphs, the attenuation ratios agree within the limits of ±1 standard deviation. At the lower graphs, we can see small deviations from the unity, which are mainly due to the stronger effect of noise for the lower signal and to the high sensitivity to the daytime, as we will see in the following. We know that we showed that signal from different sources for the same filter may differ by more than 3 orders of magnitude. Thus, thus the effect of the daytime on the calculated attenuation is different in each case. We also know that the transmittance of neutral density filters is independent from the intensity. Thus, measurements of the attenuation with different intensities might be used as an evidence for the validity of the daytime. So what we show here is the graphs are the same as in the following slide. We see the ratio of the attenuation for the filter 2 to the filter 1, but we used 3 different values of daytime to calculate the final result. What we ended up to is that a 10 nanosecond difference in the daytime leads to 1 to 3% difference for the attenuation from the direct sun measurements. And on, I think, obvious difference for our final results. This slide is about the spectral stability monitoring. At Thessaloniki during the 6 last years, to monitor the spectral stability of the instrument, we perform a scan of the internal mercury lamp at the slits 0 to 5. Then we calculate the step where the lines at 297 and 334 nanometers are found at. And here we present the results. We present the difference from the mean calculated value for the step of 297 nanometers line and 334 nanometers line. It is obvious that we have very large variations at the lower wavelength. Also, we can see that we checked what was the cause of these variations, and we didn't find them to be directly related to any temperature or signal variations. But they are generally in good agreement with the variations of wavelength shift as they are calculated by the SIC algorithm. This slide is about the measurement of spectral lines from the diffuser and from the quartz window. We performed measurements through the diffuser and through 3 different positions of the quartz window, of the zenith prism. Then we calculated the step for the mercury and the cadmium lines on slits 0 to 5, and the results are here. In the left graph, we can see the difference between the calculated step through the diffuser and through the quartz window with respect to the calculated step through the diffuser. while at the second graph, we can see the same difference in respect to wavelength. In general, we see differences up to 6 steps, and there is a suspicion of a specific pattern when the position of the zenith prism was horizontal. But since a large part of these results are recent, we need to do more work to define the reason for these deviations. In this final slide, you can see we try to check the dispersion coefficients when they from a quadratic and from a cubic fit. In the upper graphs, you can see the quadratic and the cubic fit of the lines of mercury and cadmium. The results are from for slit 1 of the double monochromator Brewer number 86. And in the lower graphs, you can see the corresponding residuals for each case. As we can see here, the residuals are generally lower when the third order polynomial fit is used. So we expected that we would see a similar results to our spectra when they would be applied. So we expected lower wavelength shift values when the third order polynomials would be applied. But as you can see, this is a representative spectra, some representative spectrums in my opinion. As you can see here, when we applied these results, the plot number A is for the second degree polynomial, while the plot B is for the cubic fit. When we applied these results, we didn't find any important difference. So according to our results, there is no important improvement when the dispersion coefficients from a cubic fit are applied. And this was all. Yes, please. I know, and okay. I mainly saw them because I needed some, yeah. Okay. Some feedback.
Anyway, okay, now it's working. So about the last, if you just go back, here.
This one.
I'm curious, how did you actually apply the cubic and quadratic?
Okay. We know the step for each measurement. So I got the spectrums we already had, and then I got the step and converted it to wavelength using the cubic and the quadratic, which was already applied.
Okay.
You understood what?
Yeah.
Okay. And then I processed it, these spectrums and a lot of others, with the SIC algorithm. So that was the way.
Okay. So you didn't actually measure using the dispersion.
Yeah, that's right.
Okay.
That's correct.
Okay, that's fine. Now, what will the dead time? I'm trying to remember what. The dead time. I know that 86 has unfortunately very low sensitivity.
Yeah, okay.
So, but still, it has an increased sensitivity towards larger wavelengths, right?
Yeah,
just like all
Mark
IIIs have.
Mm-hmm.
Have you tried moving the micrometer to the end and measure the dead time there?
Yeah, of course.
And it's still not enough light?
You mean, okay, you mean about the lamp?
Yeah, for the standard
I get better results because the results, okay, I will go back.
Yeah.
Here, I think. The results for the lamp are with filter number 1, on the filter wheel 2, I think.
Oh.
So I get better results if I do it with zero. Yeah.
Yes.
So that's what I should do.
Okay.
But
yes, I think you should. Yes.
I recently discovered.
Okay. Okay.
It would be good to join the presentation and then this together.
No problem.
Yeah, that's
if
fine.
It's a similar
if you could just
presentation.
remind me what you did with the neutral density. I think
Okay.
just quickly.
Yeah, it needs much more conversation, but I didn't have time to do it.
Okay, I'll try to remember what I had about
We
this.
used as different version of SS routine and to calculate from the sun, but I can't explain it in 5 minutes.
No, I had another one. About the HG tests.
Yeah.
How did you
The HH
measure the
yeah.
shifts that you showed?
The HH test. You
Yeah,
mean.
yeah,
We make a scan of the mercury spectrum at all the 5 slits. And then I apply the same techniques more or less that are described in many studies. You know, I get the slopes for the 20 to 80% of counts and get the central,
Okay.
you know, find the center and all that stuff. But,
We'll have to discuss that.
okay, yeah. So, yeah.
You described, I couldn't tell what curve was which. I presume on that mercury line position test that the odd line out was the,
That
was
was,
the
okay.
diffuser?
That, you mean there was a large difference?
Well, there were several lines that were together.
Yeah.
And one that was quite displaced.
Okay, okay.
Which one was the displaced one?
Well, I'm not sure. You mean about the wavelength accuracy?
Where you were doing the mercury lamp test at different angles of the prism
Okay, this one. Okay,
through the
so-
window.
Sorry, yeah.
And then you did it through the diffuser.
Yeah, sorry.
Which one was the odd curve?
The curve of the lines.
Well, several of them were in the same, pretty much on top of each other.
Okay, yeah.
One of them was displaced.
Yeah. That was, I think, for the horizontal position of the quartz window. That was, the step was displaced. It was lower than, higher than,
Okay, there's two comments about that. One is the question of whether you're filling the field of view of the instrument
yeah.
uniformly in all positions.
And no.
My suspicion would
Yeah.
be that the diffuser might give a different answer than all of the direct views if
That-
there's an issue about filling the field.
That's why.
But furthermore, some brewers actually have the window or the prism entry partly obscured when it's actually at 90 degrees
Okay,
because
so
of the height of the instrument
Yeah,
inside the
yeah,
box. So you have
that
to
might
look
be the
at
reason.
these.
And
Yeah.
that's what I said. I needed some feedback. So that's why I presented this result. So